Hello everyone. Today we're getting deeper into vectors by introducing another useful idea, vector projections. It's an idea that can take a little getting used to, so we'll break it down logically. This video will firstly introduce the idea behind vector projections, using plenty of vector diagrams to make that clear. We'll then pull up the formula for vector projections and go about proving that formula. In an upcoming lesson, we'll start applying vector projections to some examples. Let's go. Right from the beginning of vectors, we've been using the idea of splitting vectors into components. That is, their horizontal and vertical components. That's where all of this I and j vector notation comes from, with I being the unit vector in the x direction and j being the unit vector in the y direction. We can extend this idea by splitting a vector into components with respect to another vector. What I mean by this is, let's consider two vectors, a and b, with an angle of theta between them. We want to split A into two components. One component parallel to vector B, like this. Let's call this component U. The other component will be perpendicular to vector B, like this. We'll call this component W. By vector addition, we know that U plus W is indeed A. And now we can define the projection. The projection of A onto B is the component of A lying parallel to B. So it's U. The projection of one vector onto another vector will be a vector. This is the conventional notation to denote the projection of A onto B. You write the word proj and then a little vector B in the subscript and then a big vector A. Notice the importance of the order. This is not the same as the projection of B onto A. If we look to our diagram, that would be some vector up here in the direction of A. It is a common mistake to get them mixed up, so always remember which vector you're projecting onto. Here, in our original situation, we are projecting A onto B. A nice way I like to remember it is that the projection of A onto B is like the shadow that vector A would produce on vector B if there was a lamp or something directly above. Just note that the face of the lamp is oriented so that it is parallel to vector B. If that works for you, lovely. Okay, so we have an understanding of what vector projections are. Do we have a nice formula to match? As is the case most of the time in maths, yes we do. Here is our formula. Soak it in. This part of the formula is just a scalar, since the dot product produces a scalar. So the projection of A onto B is just some scalar multiple of the vector B, which makes perfect sense since it is parallel to B just with a different magnitude. Let's see exactly where this comes from with a nice clean proof. It'll involve some knowledge of parallel and perpendicular vectors, so make sure you're sweet with those. Let's pull up our diagram from before and remember that we've denoted the projection of A onto B with the vector U. We know that U will just be some scalar multiple of B, so we'll denote it as KB, where K is just some scalar. We want to find K to fully describe our projection. Now, since U plus W is equal to our vector A, we can rearrange to make W the subject. And let's sub in that U is equal to K times B. This next step is the cheeky step. We set this all up so that vector W is perpendicular to vector B. Just look at our diagram. And recall that when two vectors are perpendicular, their dot product is 0. So W dot B is 0. Or A minus KB dot B is 0. You can then expand the dot product like you would a regular number using this special property of the dot product. You just take the dot product of each individual term in the expansion and add them, or minus them in our case. Remember, what we're trying to do is identify what k is, and now we're in a position to do that because we have a simple equation involving k. So let's make k the subject. We can do this by taking this to one side and then dividing by a factor of b dot b. And there we have k. Alright, great. And that now means that U is equal to this. And since we know that the projection of A onto B is just U as in the setup, this is our projection formula. Really good stuff. A nice 3-step summary of that proof would be: 1. Break A up into parallel and perpendicular components with respect to vector B. Note, a more jargon-heavy way of saying this is resolving A into rectangular components. Next step, 2. Use the perpendicular dot product rule between W and B. And 3. Solve for k and write out our full projection formula. Nice. Just before we wrap up, there is one other term that you may hear used in the context of vector projections. The vector resolute of A in the direction of B is equivalent to saying the projection of A onto B. They're literally just synonyms, but the word projection is definitely more widespread. Let's sum up this fairly packed video. We journeyed into the idea of a vector projection, essentially splitting up a vector into parallel and perpendicular components with respect to another vector. A formula for the vector projection followed. It's an important one. Be extra careful with the notation for the projection of A onto B. We went about proving that formula through this 3-step process. A little extra terminology rounded up this content. In an upcoming lesson, we'll start to see how vector projections look in some examples. That's really important to consolidate this content. I'll see you all for that.